Non, sinon, le bâton. Je suis pas sûr qu'il marche. Je sais pas si
Hello?
S'il faut manger.
On demande si c'est pas la clé que derrière l'ordi.
On peut commencer. Okay, so let's start the afternoon session with Yuxiao Xie from Pascal. We're going to talk about introduction to compactified imaginary Liouville theory.
Thank you. It's a great pleasure to give a talk at this nice conference in the last 2 weeks. You can see that I'm based here, so I can attend this whole conference. So today, my plan is to give a very brief introduction to compactified imaginary Liouville theory. So if you were here last week, we had the lectures of Rhodes, who already introduced real Liouville theory, and also at the end, we briefly mentioned some ideas in this theory. And there was also Romain's talk, who's here, who also mentioned about this theory. But for him, it was the more interesting case was the non-compactified version of the theory, which is more difficult. But here we're in the compactified case, and it's easier, and we know more things about this theory. So okay, so let's start. So first, let's briefly review what real Liouville theory is. So for us, a CFT would basically be the data of some correlation functions that you can define on any surface, and they are going to satisfy some conformal invariance properties. And we would like to construct these correlation functions by realizing such a path integral. And in the real Liouville theory, we consider this path integral. So you begin with a Riemannian surface, so a surface of dimension 2 with a conformal metric on it, and you consider this Liouville action, which has 3 parts. So first you have the standard Dirichlet energy, and then you have this linear term. Here kg is the curvature of the metric, the scalar curvature. So this represents the background charge of the theory. And then finally you have this exponential term, which is the Liouville potential. So we have this action, and we'd like to realize this path integral, integrating against these vertex operators, which are the standard ones that everybody is familiar with. So they're going to correspond to the primary states in your theory. And here we have some parameters. Mu is a positive number and gamma is between 0 and 2. So this is for technical reasons for convergence. And then Q is coupled to gamma by this formula, and you also take some real charges. So that's real Liouville theory. And there are a lot of people working on it, and we already know a lot about this theory. But now today, I'm going to focus on an imaginary version of this. So what changes here is that we're going to take gamma to be imaginary, but we would like to work with real numbers. So we actually change our parameters. So I replace gamma by I beta, where beta is a real number. And then I also replace Q by IQ, where Q again is a real number. But now the relation between these two is changed like this. And then we also change the charges to be I alpha j, where alpha j, so that alpha j can be real. So that would basically be what imaginary Liouville theory is. But here we have this twist that we make the theory to be compactified, which means that our field, instead of taking values in R, we're going to let it take values in the compactified R, which is the circle radius R that we can choose, which I will come to in a minute. So that's the definition of imaginary Liouville theory in the compactified case. So why do we do the compactification? So this actually comes from a simple calculation. So normally to do a path integral like that, you would decompose your field into 2 parts. You have the constant part, which we call the 0 mode C. And then you have another part, which is a part with average 0. So we have like probabilistic tools to deal with the mean zero part. But if you just look at the integral as an integral in the zero mode C, you see that it has this form. So here A and B, they're related to the other parameters by these formulas. So you can see that since I have an I here, both these terms are going to be kind of periodic in some sense. So this means that if you want to integrate over R, this will almost never make sense. But what can let it make sense is if you just integrate over a finite interval. And if you want this to be well-defined, you should assume that both of these functions, they are going to be periodic with respect to the interval that you're integrating over. So we introduce this compactification radius, which is a real positive real number, and we assume that all the parameters of our theory are going to be rational with respect to this compactification radius. So specifically, we make this assumption. Now, this simple assumption has important consequences on the CFT structure. So first, yes.
So you motivated why you introduce R, but is there also a version of this imaginary field Liouville theory where R is still infinite, where it takes values on the real line?
Yes, so that's exactly what non-compactified imaginary Liouville theory is about. And basically in that case, sorry.
Does that exist as in this probabilistic setting?
As of now, I don't think there is a mathematical construction of it. But basically the idea would be to not integrate over R, because that would not make it make sense. Instead, you have to integrate over a complicated contour on a complex plane. So, and we expect that to turn into a fully developed mathematical theory, but this is still work in progress. And this was also partly explained by Homa last week.
Okay.
Yeah, any other questions? Okay, if not, let me deal with the simpler compactified case. Right, so you can actually see that this CFT is not going to be a unitary CFT because of the imaginary part. And also, if you put these two conditions together, so remember that Q is related to beta by this formula. So you can see that these together would imply that you have some rational quadratic equation in beta, which means that your center charge, you can actually compute it to be 1 minus 6q squared. This is going to be a rational number. So you no longer have a continuous set of theories. And then also we have this condition on the charge. So you can see that so you can see later that these will give you the primary field in your theory. Now we have this condition, which means that the spectrum of your theory is going to be discrete. And finally, with our assumptions, you can actually do something that mathematicians would dream to do, which is that you can Taylor expand this part. So if you Taylor expand this part, you collect the terms, you find that your integral has a very simple expression in terms of the b before. You only pick up one coefficient here, and we will see later that this. So since you have a probabilistic construction for this integral, it's going to be an expectation, which is just an integral over the corresponding infinite dimensional space. Okay, so that's a very brief introduction to what compactified imaginary Liouville theory is. Any questions?
So the q squared is now positive, right? So this will walk also through the minimal model central charges, or is that range? Oh no, it was a -2, right? That was the bound.
Yeah. So actually, C is going to be less than -2, and this is because of this restriction on beta, which is for convergence purposes. We can only deal with the case where beta is less than square root of 2.
But you could still have some non-unitary minimal models with that, right?
Yeah, but I'm not an expert on minimal models, so I'm not sure about that.
Okay.
Yeah.
Unitary or non-unitary?
Some non-unitary minimal models, like, I don't know, Liang with -22/5, and then one could ask, how does that theory differ from the corresponding?
Yeah, of course.
Yeah, but we'll see that this theory is not going to be a minimal model because it's actually logarithmic. Okay, so the next part of the talk will be to introduce some of the key ideas involved in the mathematical construction of the path integral. So first of all, there is a topological ingredient in this construction, which is that it's not possible to write your field as C plus something which has the average 0, because now we're working with maps that take values in the compactified circle. So not all maps of that form are going to be contractible. So So you have some non-trivial topology that you have to deal with. So what you can do is that you can consider the set of free homotopy classes between these two spaces, and you can find that you have a natural representation for it, which is the first cohomology of your surface. So we have this natural map. So basically, this means that if you take a closed one form with integral cycles on your surface, and then you integrate with respect to a base point x0, you get some non-trivial continuous map from sigma to this space, and then you should add this part in your path integral. So we arrive at the formula, the decomposition for the compactified free field. So you have a constant part which takes values in this circle. You have another part which can be dealt with using probabilistic methods. It's built with something called the Gaussian free field. So this morning we heard about the discrete Gaussian free field, but this is a continuous version. So this basically gives you this part. So it gives you this Gaussian integral on the infinite dimensional space of functions with mean zero. And then you have this topological part. And what you should do is you should integrate over all three parts. So we arrive at the definition of, it's too slow. Right, so we arrive at the definition of the path integral where you put just the Dirichlet energy term. So if you just put the Dirichlet energy term, you have a sum of three parts. You have the integral over the GFF over the part with mean zero. You have the integral over zero mode. You also have the sum over the set of all possible topological classes of your field. And then you can define this path integral and you can verify this. This already gives you a CFT, but it's a trivial one. It's the free field, which has central charge 1. So you have this formula. So if you change your metric to a conformal one, you get this wild anomaly. Okay, so that already gives you the free theory. But now we want to add in the other terms. So in the potential, we already have this quadratic term, which is the free theory. Now we want to add this linear term. But the linear term has additional topological complications. It's because now phi is a field that takes values in the circle. So it's not possible to just multiply by a real number and then integrate. It doesn't make sense. So the idea would be to integrate instead over something which is we would like it to be simply connected so that you can make sense of this integral as a well-defined function. But you find that it's actually sufficient to assume that the domain has trivial first homology, which is what we do here. So basically, the idea is that you choose some simple closed curves and you cut the surface with respect to these curves, and you obtain a domain where you can actually perform this integral in a non-ambiguous way. And then you define the integral as the integral over the remainder over this domain. But then you find that this is going to depend on the curves that you chose. So if you perturb the curves a little bit and you do some Gauss-Bonnet calculations, you find that you're going to need to add some additional regularization terms so that it can only so that it can be well defined. So we add in these terms, and we have this definition with respect to such a family of cutting curves. And now the proposition is that if you change your family, you're going to arrive at something which is not exactly equal to your original integral, but it's only going to differ by some integral part. And in the end, this is going to mean that this exponential part is going to be well defined. So we have a definition for this part now. Okay, so that's how you make sense of the linear term, of the curvature term in the path integral. This idea was already used in physics and in mathematics before, but not in this form. This form is especially suitable for studying, for example, the Seagal's axioms. Like if you want to glue two surfaces, it's easier to work with such families of cutting curves instead of a fundamental domain. You can do it with a fundamental domain too. Okay, so we also have this exponential term. So we have two exponential terms here. So first you have the vertex operators, and then you also have the Liouville potential. They're of the same form with different beta, with different parameters. But there's also another probabilistic tool that you can use to define this. This is called the imaginary Gaussian multiplicative chaos. I don't have the time to go into the technical details of this, but in any case, so this can be realized if you assume that beta is between 0 and the square root of 2. And then you can also add in these vertex operators. And to have convergence, you should also assume that they are bigger than Q in this case. Remember that Q is a negative real number. Okay, so now we have a working definition of the path integral, and we can actually prove that this is a CFT in the following sense. So again, we have this Weyl anomaly formula, which says that if you change your metric to a conformal one, you're going to have this conformal vector. So in this vector, you see your central charge of the theory, which in this case is 1 minus 6q squared, and you also have some you also get this term where you see the conformal weights of these vertex operators. So in this sense, we consider it to be a conformal field theory. Any questions on this? Okay, good. Okay, now I'm going to introduce some generalizations to the construction that I just did.
Can I ask a technical question on that? So you're not working with local coordinates around the insertion. No. So there should be some implicit local coordinates defined in terms of the metric. You know what these would be?
What do you mean by?
If I want to translate this into the formalism where you do have local coordinates, then to get that transformation behavior, I would first sort of map the correlator and then retransform the local coordinate. That would give this factor. So there should so from this point of view, there should be a way to generate the local coordinates out of the metric so that it reproduces the formalism with local coordinates.
I think what you're saying is that when you take a local coordinates, you can assume your metric to be the standard flat metric, and then you have this conformal factor between your real metric and this flat metric. So that would be how you get into coordinates.
Yeah, maybe that one.
Yeah. Okay. Okay. So as I said, I'm going to introduce some generalization to the construction. So the first thing that you can do is you can actually add in more topology. So you can assume that your field has a non-trivial winding number around each of the marked points. So if you do this, you find that you need to specify a tangent vector at this point, because otherwise it wouldn't make sense to consider the value of the field at this point. So if you add in this Vj, you can make sense of this as the limit of the field when you approach this point from the direction specified by Vj. And then this is what we call an electromagnetic operator. And we consider the alphas before to be the electric charge and the winding numbers here to be the magnetic charge. So there is this T duality which says that there should be dual in some sense, but this is not, it's not clear how you would realize this in the path integral in the Liouville case. Okay, so when you add this, this changes your conformal weight by this factor. And then you also have a new phenomenon, which is the spin. So if you rotate these vectors, you're going to get a phase. So what this means is your CFT is going to be a non-diagonal one. So the chiral part and the anti-chiral parts are going to have different representations.
If you rotate by 2 pi, the phase goes away, right?
Yeah, if you assume that the alpha j's are irrational, which is what we do.
Okay.
Yeah, of course, because correlation functions, they're well-defined functions. Yeah. Yeah, another thing you can do is consider the boundary CFT. So this is where you instead of working with a closed surface, you assume that your surface has some non-trivial boundary, and then you integrate over fields that satisfy this Neumann boundary condition. In this case, you have this you have additional terms in your action. So you have this boundary curvature term plus a boundary potential term. So in this sense, you can define a boundary CFT, which is important in a number of ways.
Neumann was just a choice, or?
Yeah, you can also do other boundary conditions, which is what we're arriving at next.
Can I also ask the thing? So you have this. No, this is the action. That's not nice, right? I was confused.
Okay. Okay, so you can also deal with Dirichlet boundary condition, but that would give you the Siegel's amplitude. So the idea is that you work with the Dirichlet boundary condition. So you put some boundary values, which are boundary fields, and then you integrate over fields that satisfy this condition. So in this case, you get not just functions on your surface, but functions that depend on the boundary values. So according to Siegel's idea, you should interpret this function as the integral kernel of some amplitude operator between powers of the Hilbert space of L2 functions on the boundary field. So in this sense, you can show that this theory actually satisfies Siegel's axioms. So roughly speaking, or in the sense, in the spirit of TQFT, you can state this as a functor from the cobordism category of Riemann surfaces to the category of Hilbert spaces. This functor is projective in the sense that everything is up to a multiplicative constant. So if you glue two things, they are not going to be exactly equal, but they're going to differ by some constant. And the full theory is in this paper by Guillarmou, one of the organizers, and Kupiniainen and Rhodes, who were here last week. This is for the ordinary CFT without the Neumann boundary. The case with Neumann boundary is worked by myself and Yuxiao here. We already have a paper. It's almost finished. Just have to work on the introduction. We hope that this will appear soon.
But if you were working not with Riemann surfaces, but with actual metric surfaces, the projectivity goes away.
With
the surface is a metric.
Mm-hmm.
Then the projectivity goes away.
What do you mean by surface with metric? Because on the surface, it's equivalent to put a metric and to put a conformal structure.
Well, no, because if you pick two different metrics,
Mm-hmm.
which gives the same conformal structure, amplitude difference by Weyl factor. Yes.
Yes.
And so that's the source of the projectivity, I'm thinking.
Mm-hmm.
And so I'm asking, if I do now work with a metric rather than just with a conformal class of metrics, does that make the projectivity go away? Do you then get an honest functor?
No.
Okay.
So actually, if you cut your surface into two parts and then you do the gluing, which is the composition in this category, there will be a factor of a factor that's not. So there would be something like 1 over square root of 2, something like that. I mean, it's kind of mysterious, but you do have this factor. So it's not going to be, and also this factor is not it's not just a phase because it doesn't have modulus 1.
Okay. I'd be curious to discuss that more.
Yeah, of course. Okay, so I just put a picture here. So this is like an illustration of the most complicated case that you can consider this path integral. So on a very general surface, you can have boundaries, and you can also have corners on your surface. So some boundaries, you can put the Dirichlet boundary condition. Others, you can put the Neumann. And sometimes you can have a boundary component which contains both Dirichlet parts and Neumann parts, which is why we call them mixed boundaries. And in the interior of your surface, you can put some insertion points together with some tangent vectors. And then to make sense of the curvature term here, you have to cut your surface into you have to kill the topology of your surface. And in the most general case, you can choose these and these A's and B's to cut your surface. So that's one illustration of the most general case they can do.
Sorry, what do these corner points correspond to? How should I think about them?
They're just the intersections between the Neumann part and the Dirichlet part.
Do you have at these intersections field insertions that change the boundary conditions?
Sorry?
If you want to change a boundary condition from Dirichlet to Neumann, do you need to have a field insertion of a boundary field at this place?
We don't know. We can't really change from one boundary condition to the other because here, like the Neumann boundary condition is really corresponds to the boundary CFTs, while the Dirichlet boundary conditions is what gives you the Siegel's amplitude. So their roles are not symmetric. You can't just change from one to the other.
I'm not sure if I parameterized and which are not parameterized.
That's exactly the good question.
Yeah, the D are parameterized.
The D are parameterized. Okay.
Yes.
But there is also maybe I can make a comment, there is also this constant mu in the action.
Yes, yes. So
And
in the
this kind-
boundary, so in the boundary version, what you can do is you can also put some potential on the Neumann boundary, not on the Dirichlet boundary.
And the mu can have jump at the insertion.
Yeah, so in general, the mu can be piecewise constant.
So if you change the mu, will this be a transition to another boundary condition then?
In some sense, it's related to
Yes. And can you have boundary fields when you change the boundary condition? Because it would be very interesting to study them.
Yeah, that's a good question, but I don't think we have any idea
Okay.
on this.
We can note questions, that's why we have a workshop.
Yes, exactly. Any other questions? Before I go into the part where I describe some of the facts known about this theory. Okay, so in the last part, I'm just going to give you some of the things that we know about this theory. So most questions about this theory are wide open right now, but we do know some things. So for example, we know this 3-point structure constant. So if you consider the sphere with 3 points, you can actually compute this path integral. It has this explicit formula. It's very complicated, but you do have a formula for it. And this formula is actually important because it appears also in other places. For example, this also appears as certain formulas for statistics of conformal loop ensembles that you can check out this paper where they prove this mathematically. And this is also why we expect the theory to have connections to models in statistical physics. But then for the boundary CFT, the structure constants will be integrals like this. So there will be finite dimensional integrals, but we don't know the exact value of these integrals except in very special cases. So there is this case. So if you consider the boundary 1 point structure constant, which is where you put 1 point in the interior and 1 point in the boundary, and you also assume that there is no potential in the interior. As I said, so in the boundary case, you can put potentials either on the boundary or in the interior, or both. So here, if you assume that there is no potential in the interior, you can find that the integral has a very simple form, which you can compute explicitly in this case. But we do not know all of the structure constant for the boundary CFT.
So when you say no potential in the interior, what does that mean? It's a free boson in the interior?
That just means that you put mu to be 0 here.
Okay.
So then you have 2 mu's, one in the interior and the other on the boundary.
Okay.
So if you put the interior mu to be 0, this is what you have here. It's still not a free theory because you can put mu non-trivial on the boundary. So basically, the problem is when you have both of the mu's to be non-zero. In that case, this will be a very complicated integral that there is no non-formula. Okay, so about the algebraic structure, as I said, this is a non-trivial. This is a non-unitary CFT, and so the advantage with the Siegel's approach is that you can have explicit Hilbert spaces with explicit representations of all your Virasoro operators as unbounded operators acting on your Hilbert space. So you can actually have an explicit formula for the Hamiltonian, for example, which corresponds to the L0 in the Virasoro representation. And you can show that this operator has compact resolvent with an explicit spectrum, which is discrete and real. So this is non-unitary, but its spectrum is real. And the spectrum is the same as the free theory, which is where you put mu to be 0. So putting this mu, while this makes your whole theory a lot more complicated, this doesn't really change the spectrum of your theory. And then finally, you can show that this operator is not diagonalizable. So you can actually construct explicit drawdown blocks for this operator, which means that this is going to be a logarithmic CFT.
So I can ask a question there. So this is for the, so that's a spectrum on the state space of the circle. What happens if you do state space on an interval? Do you also get Jordan blocks?
I think so.
Okay.
It doesn't have to do with the, it's more about the potential itself. So on the boundary, you also have a potential like this, which is why you can also have drawdown blocks. Okay, so what can be done for this theory now is first to find out all the structure constants of the boundary CFT. And second would be to clarify the Virasoro structure of this theory. So we already have a very concrete representation, and we can construct some concrete drawdown blocks for it, but it's very hard to classify this as a module of the Virasoro algebra. After this, we can hope to solve the conformal bootstrap of this theory, which is still open now. And then, as I said, so we expect connections with, for example, generalized minimal models, because so they're not going to be minimal models because they're logarithmic, but there might be relations with generalized minimal models, and there could also be relations with statistical mechanics models like critical loop models or the conformal loop ensembles, which I just mentioned, and also the SLE, the Schramm-Liouville evolution. And that concludes my talk. Thank you for listening.
Questions?
Can you write explicitly Virasoro action? Can you write Virasoro action?
Yes, yes, you can write the operators explicitly. Yes.
So if you look at surfaces with boundary, and you look at the Weil anomaly term, then if your surface gets a corner, then you get a sort of an extra contribution to the Weil anomaly from the corner. Is that something you can see in this formalism?
Not in our case, because in our case, we assume that corners are always intersections between Neumann boundaries and Dirichlet boundaries. But if you put both Neumann boundaries, then you could have corner terms.
Okay.
We have drawdown blocks of weight 0?
The what?
Of the conformal weight 0.
The drawdown blocks?
Yeah.
No.
Oh, so
You have
so vacuum
infinitely
is
many.
huh?
You have infinitely many drawdown blocks.
He was asking the weight, the eigenvalue.
0, 0 again. Value.
Alpha equals 0.
No. So we expect infinitely many alpha. So for alpha less than Q, we expect infinitely many alphas for which there is a drawdown block with conformal weight alpha.
Yeah, this I understand. But for the conformal weight 2,0 energy momentum tensor, how many logarithmic partners you have? This is
For alpha bigger than.
I don't know in terms of your alpha, in terms of conformal weights. HH bar 2,0 energy momentum tensor. It's part of your game, right? Conformal vector.
Maybe not, because continuous spectrum, not all
No.
fields present.
No, it's discrete.
But it's discrete here. I see. So we should have this first tensor.
Well, this has to be checked.
Ah,
Here.
I believe it's rank 2.
Yes.
So can you compute a 3-point function when there is a magnetic?
Yes, yes, you can do that.
So does it have to do with imaginary density formula or some derivative?
Yeah, yes, you can write this in terms of the imaginary dot formula, but it's more complicated than dot formula.
Basically, you can just remove the residue of some pores of the dot formula, and then you kind of get the correlation function when you put a Jordan partner, the 3-point function. Just try to remove the singularity.
Yeah, so you had this formula where you do the expansion of the exponential, right? And you say you're allowed to do this in this setting. Did I get that right? So you can take your interaction term there.
Yes.
And you can expand out the like like you would do conformal perturbation theory usually. And you're saying these integrals are all well defined and converge. That's good. And that defines the same theory, is what you're saying.
Yes. So this theory is perturbative in terms of mu. And actually, we had this neutrality condition before, which says that you should let me find it. Okay, so it's here. So we have this neutrality condition. So actually here, if you choose your parameters so that P is exactly 0 here, you get the free theory.
Okay. I can't parse it, but you can explain that to me later.
Yes, of course. So this means that all the free correlation functions are part of the correlation functions here. So there are special cases of the correlation functions here.
Okay.
Okay, so maybe we thank the speaker again.